Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on August 7th, 2025, so just yesterday. This paper finds that even state-of-the-art vision language models, which are AIs that can understand both images and text, often fail to perform better than random guessing on tasks requiring a real grasp of physics. The paper is titled DeepPHY, Benchmarking Agentic VLMs on Physical Reasoning, and it really paints a clear picture of where these models currently fall short. Essentially, the authors created a new benchmark to test if these models can translate what they know about the physical world into precise, successful actions. Also, the authors shared their implementation, and the entire DeepPHY benchmark is available on GitHub. You'll find the full framework there, including the installation guides and all the evaluation scripts for the different physics environments, so you can actually run these challenging tests on other models. Alright, so this figure lays out the entire DeepPHY benchmark suite. In the middle, you have a radar chart comparing different vision language models. And surrounding it are the 6 different physics-based games they were tested on, like Angry Birds and Cut the Rope. The numbers in parentheses show the success rate for the best model on each task. You can see that even for the top models, performance is often quite low. For instance, just 26.1% on Cut the Rope, which really shows the significant challenge these tasks represent. This table then details why each of these environments is so uniquely challenging. It breaks them down across 5 key dimensions, from the fundamental physics involved to the complexity of the agent's actions and the reasoning required. For example, you can see how tasks like iFire and Cut the Rope test for understanding complex dynamics like tension from ropes and springs, which aren't a factor in the other games. This variety is what makes the overall benchmark so comprehensive, testing models from multiple angles. Now, to make these complex games playable for an AI, the authors had to standardize the inputs and outputs. This table shows exactly how they did that. For the input or observation space, the models see a simplified view, like an image with a helpful 5x5 grid overlaid. For the output or action space, continuous human controls are converted into discrete commands. For instance, in Angry Birds, the model just has to generate Python code specifying the launch angle and power. Okay, moving to the results. These charts show performance on 2 specific tasks. The top graph is for the fire environment, and success rates here are quite low. The stacked bars show cumulative success after 10 attempts, and even the best model, GPT-03, only reaches about 23%. This really highlights how models struggle to learn from failure. In contrast, the bottom graph for iFire shows much stronger performance, with top models reaching over 80% success, suggesting they can handle its specific temporal planning challenges. This table then shows the performance on Pool Tool, Angry Birds, and Cut the Rope. Now, the results for Pool Tool look impressive, with models like GPT-40 Mini hitting a 100% success rate. But the authors note this is a bit misleading. The models use simple, brute force tactics, not nuanced physics. And when you look at the more complex games like Angry Birds and Cut the Rope, the story changes. There's a huge performance gap compared to the human baseline, showing multi-stage planning is still a massive hurdle. So to wrap things up, the key takeaway is this fundamental disconnect. Models might be able to describe physics, but they struggle to translate that knowledge into precise, successful actions. The DeepPHY benchmark really shines a light on that gap. That's it for